Hi, Andrea here. Today we will deep dive into the magic of the induction principle. It is the key not only to build the set of all natural numbers, but also to ensure the behavior of such class of numbers. Therefore, we discuss about its implications. Up to now, we have discussed the successor operation, which is counting forward. That has been presented as the basic brick to build the addition operation, namely counting forward many times. To have a clear idea of such framework, the expression 0 plus n is surely equal to n, because it is like applying the successor operation n times to our starting point 0, and the result is n itself. Moreover, the sum of S of n plus m can also be seen as successor operations concatenated. We can say that S of n plus m can be written simply applying other m times the successor operation to S of n, obtaining something like this: S of S of S of S of n. It is a little fancy, but to conclude, it is simply a first S followed by m times S. Therefore, it is S of n plus m. Nice! We got these two relations as base for the addition operation. This is amazing, but incomplete. Let's say, what happens in the opposite case of the first formula we got? What is the result of n plus 0? It can seem trivial. The result is again n, but no one told us that n plus 0 is equal to 0 plus n. I want to show you this is not something we have to assume. It is something we can prove thanks to induction. Before starting, let's remind the main points of the induction principle. Given certain property to assess, if the property is true for 0, if the property is true for S of n, assuming it true for n, then the property is true for every n. Given the first two pieces, we get a general validation of the property. So, first thing first, let's see if n plus 0 equals n is true when n is 0. Now, our expression becomes 0 plus 0 equals 0. But this is a particular case of 0 plus n equals n, again with n equal to 0. Therefore, we figured out the property is true for 0. Now, assuming that n plus 0 equals n is true for a given and fixed n, is it true also for its successor S of n? Well, the expression n plus 0 becomes S of n plus 0, which is equal to S of n plus 0, thanks to our second formula. Now we are assuming for a moment that the property is equal for our particular n, and so n plus 0 is equal to n, and we get S of n. You see, we got the exact same expression using the successor of n. For the induction principle, n plus 0 equals n is true for any natural number n. Now, it is possible to show in the same way that n plus S of m equals S of n plus m. This is the inverse case of our second formula. We can induct over n, keeping m fixed. Again, the starting point is n equals 0. In this case, the left part of the starting expression becomes 0 plus S of m, and it is known that 0 plus a number is that number. So 0 plus S of m equals S of m. On the other hand, the right part is instead S of 0 plus m, and for the same reason it is again S of m. Thus, the equality is true for n equals 0. Fast forward, assuming the expression n plus S of m equals S of n plus m for a given n, is it true for S of n? The expression becomes S of n plus S of m equals S of n plus m, where we have just switched n with S of n. We must prove it. By the second property of addition, S of n plus S of m can be written as S of n plus S of m. Now, we are assuming the property true for a generic m and n. So, we can rewrite the internal part of the expression obtaining S of m plus n. The other side, S of n plus m, can be written using again the second property of addition as S of n plus m. The two terms of the equation are equal, so the n plus S of m equals S of n plus m is always true by the induction principle. Fantastic! These two affirmations surely show a first use of the induction principle, but they are the basis for more important results. For this reason, they get a special name. In fact, an easily proved claim helpful for proving other claims is known as lemma. Therefore, we have lemma 1 and lemma 2. So, what are these more important results? One of them is the commutative property of addition. Namely, it means we can commute or also invert the first and the second number in a sum. Let's prove this using the lemmas. As always, we start considering the case n equals 0, with the other natural number m fixed to a generic value. The commutative property becomes 0 plus m equals m plus 0. Is it true? Well, the left term is, by definition, summing starting from 0. The right term, by the first lemma, is again m, so the property is true for n equals 0. Now, let's consider n plus m equals m plus n, true for a given n, and let's see if it is true also for the successor of n. We have to prove S of n plus m equals m plus S of n. By definition of addition, the right term is equal to S of n plus m, while the second term, by the second lemma, is S of m plus n. We are done because we are assuming n plus m equals n plus m. Therefore, the property is verified. That is what I am talking about. It is not just obvious that n plus m equals m plus n. It is reasonable. I know, we have proved only one of the main properties of natural numbers. But hey, I don't forbid you to explore this topic on your own. Give a look to the following properties and try to prove them. I am sure you can do it.